Very good afternoon to all of you. And I would like to thank all the organizers to have this meeting. It is a very good meeting and also giving me this opportunity to discuss our recent work here in this platform. So this is the last talk. So I may try to use the open boundary condition if necessary, but maybe not. Maybe not. I may finish it within time. So I'll be talking about this physics of re-entrant localization transition in a quasi-periodic double-well lattice. So we are from IIT Guwahati. So Guwahati, this is one of the most beautiful picture in of IIT Guwahati. And there are several such pictures. This is a very beautiful campus. I would suggest people to visit once this pandemic gets over. And so today's talk will be on re-entrant localization transition. And for more details about the work, one can actually visit this reference, this recent article. And some of these things I may talk today, which are ongoing right now, some of these results. So let's see whether I can reach there. So this is the brief outline of the talk. So I'll first talk about this single particle localization, which is known as Anderson localization, and then I'll talk about localization in quasi-periodic lattice. Then I'll briefly introduce the double-well lattice. Then we'll study the localization in double-well lattice. Then finally, we'll see how re-entrant localization happens. And if time permits, then I will talk about possible experimental signature of this physics. Okay, so first I would like to discuss about this Anderson localization. So since I have a very big title, I will hide some parts of the title and open up slightly to show the relevant physics in respective slides. So here I'll be talking about localization transition in a lattice. And the most famous paper related to this is the first paper by Anderson in 1958, which talks about this absence of diffusion in certain random lattices. So what this paper says is that if electrons experience some random potential in a lattice, then there is the diffusion stops to occur and the transport is ceased. So that means the electron wave function can get scattered multiple times with this random potential, and then finally this electronic wave function exponentially decays within certain localization length or localization volume. So this analysis was based on this simple Hamiltonian, which has two different terms. So the first one is the random potential, and second one is the hopping between the nearest neighbor sites. These are electronic creation and annihilation operators. This is a simple problem, and of course this is in one single particle physics. So what Anderson predicted was that for a sufficiently large ratio of W by J, all the single particle states in the system are localized. Okay, so this is known as Anderson localization, and this was one of the most important findings in the last century. So it says that exponential, due to this localization, there happens some exponential decay of the wave function, and this leads to this metal to insulator transition. That means electron wave function goes from delocalized nature to localized nature. So that means your conduction diffusion stops, so that means you get some metal to insulator transition. So in this cartoon picture, you can see that this is an extended wave function. It is a normal periodic lattice where electrons can hop around between the lattice sites. But the moment you introduce some kind of disorder in the system, you can see that this electronic wave function gets exponentially localized. And this is one of the very interesting manifestation of quantum mechanics. Even though electrons have finite kinetic energy, they can actually stop by this. They can stop by this random potentials. Okay, so this was happened. This happened in 1958. But in the next 20 years, many things happened. But the most remarkable was in the year 1979, when this famous Gang of Four, where Anderson is one of them, they proposed a theory called scaling theory of localization. And in this theory, they discussed about how localization transition depends on dimension, And about this, yesterday Robin Kaiser actually discussed a lot about this picture. This is one of the most famous picture in the context of localization transition. So the key finding of this analysis is that in 1D and 2D, there exists no metal to insulator transition. So this means for any finite value of disorder potential, the system goes from, the system immediately becomes insulator. Okay. However, in 3D, there exists a transition, there exists a critical value where there occurs a metal to insulator transition. So looking at this graph here, one can understand how this thing happens. So apart from the serious analytical work behind this physics, behind this prediction, one can easily understand that for, I mean, if you define this dimensionless conductance G, which is G over E squared by H cross. So what this gang of four did was they defined this beta function, and looking at this conductance, value of conductance at different extreme regimes. For example, in metallic regime, this is the ohmic behavior of conductance, which goes as L to the power D minus 2. D is the dimension of the system. And in the insulating phase, this conductance decreases exponentially. So these are the two extreme cases in the metallic phase and in insulating phase. But if you look at this beta function, then you will see that for insulator, beta goes as log of G, for metal, beta goes as D minus 2. So, and this intermediate things has been extrapolated. So if you look at here, in this part, for dimension 2 and 1, this beta is always negative. So that means this conductance always decreases as you go on increasing the length of the system. So this arrow indicates the length of the system. In both 1 and 2D, the conductance decreases. However, in 3D, there is a transition in where this beta goes from positive to negative value. So that means there is a transition at some critical point. So this gives rise to this metal insulator transition in 3D. However, there are no transitions in 1D and 2D. Okay, so this was very important. I mean, very important finding which says that there is no transition, no metal to insulator transition in dimensions less than 3D. In the subsequent year, just in 1 year after, Aubry and Andre, they proposed that true disorder is not necessary to see single particle localization in one dimension. So what they propose is that you don't need true disorder in the system. The single particle localization can actually happen in presence of quasi-periodicity in the lattice. So quasi-periodicity meaning it is neither properly perfectly periodic nor disorder. So you can have incommensurate lattices. For example, this Hamiltonian which says that, which has two different terms again. This is the hopping matrix element between two different neighboring sites. And this is the extra term which is different, slightly different, not slightly different. This term is different from this Anderson's model, where this term has a strength, delta, and this cosine term, which gives rise to this quasi-periodicity in the system. And the quasi-periodicity can be introduced by choosing a suitable beta, and beta is in general an irrational number. And one has to choose beta in such a way that it is the ratio between two adjacent Fibonacci number. When the Fibonacci numbers are very large, then this gives you the perfect quasi-periodicity in the system. So Aubry and Andre suggested that if you have a quasi-periodic system like this, model like this, then one can actually see transition, single particle localization transition in 1D, which is completely different from Anderson's prediction. So this is one of the very important finding of Aubry and Andre. So this model has a peculiar property of self-duality. Self-duality meaning if you make the transformation of this model to momentum space, then this model is equivalent in the momentum space. So the real space and momentum space transformations are equivalent at this point when delta by j equal to 2. So that means the states which are localized in the real space are extended in the momentum space and vice versa. So that means there exists a phase transition at this critical point delta by j equal to 2. So if you look at in this cartoon picture, so if I increase this delta by j, which I call disorder strength in this case, although it is a quasi-periodic strength, so you can see that all states localized to, extended to all state localized at this delta by j equal to 2. Okay, so this is the key finding of this Aubry-Andre model. Now this can be easily seen from the energy spectrum. To see this physics from the energy spectrum, one can use this diagnostics known as this participation ratios. The first one is called inverse participation ratio, which actually indicates the localization property of this system that can give rise the extent of localization. So if the single particle states are localized, then this quantity is finite and large. And if it is extended, then this quantity is 0. And the other quantity, which is called normalized participation ratio, by definition, this is actually 0 in the localized state and it is finite in the extended state. So looking at these conditions, one can distinguish between localized and extended states. So if you plot the energy spectrum along with their IPR values, so this color bar is for IPR strengths. So you can see that this part is completely dark before delta by j equal to 2. This means these are extended states and these are localized states. So similar physics can be seen from here if you plot the eigenstate indices with respect to their IPR value. So this dark patch is this corresponds to the extended state, and the right side colorful patch is for the localized state. Now, if you take average of all these IPRs over all these states and plot them together, you can see that there is this nice sharp transition point from where this IPR becomes finite and NPR becomes 0. So this is exactly happening at delta by j equal to 2. So this is a critical point where this metal to insulator transition is happening, or all states extended to all state localized is happening. Okay. So this finding of Anderson localization in one dimension was first observed in these experiments of Alain Aspect and Massimo Inguscio. In these two experiments, where Alain Aspect used this speckle pattern to observe this localization transition. Here you can see at t equal to 0, the Bose-Einstein condensation cloud is in the trap when they release, and when in the presence of disorder, you can see that there is an exponential fall of this atomic density, which can be seen from here. The central peak is the initial position, initial atomic density. After a certain time, you can see this exponential tails indicating the localization transition. On the other hand, Massimo Inguscio's group, they constructed this bichromatic lattice, which is a quasi-periodic potential, by superimposing a deep periodic lattice with a shallow periodic lattice with a different period, which is incommensurate to the previous lattice. If you combine these two, then you get this quasi-periodic lattice. Okay. So if you load BC to this quasi-periodic lattice, a cloud of Bose-Einstein condensation, they are non-interacting particles, so you can treat them as single particle physics. So if you load them and you release the trap, then you see that this cloud is expanding in absence of disorder. It's a free expansion. But if you increase the strength of disorder, then you see that cloud is not expanding. So that means you are in the regime of Anderson localization in 1D. Okay, so these are the very fundamental observation of Anderson localization in 1D. Now, another interesting concept regarding this Anderson localization in 1D is that if you break the self-duality of this Aubrey-Andre model, then you get the concept of mobility edge. And this mobility edge is nothing but the critical energy separating the localized and the extended states. So if you break the self-duality, what will happen? Instead of all states going from extended to all state localized, what you get is that there will be a critical regime where both extended and localized states will survive. So this means in the cartoon picture, if you look at here, this is the disorder strength increasing from here. Instead of going directly from all state extended to all state localized, there will be a critical regime where both extended and localized states will survive. And the critical energy separating these two regions in an energy spectrum is known as the mobility edge. And there has been a lot of debate how to obtain this mobility edge, what kind of model one has to introduce, and so on. So there are a series of papers proposing the existence of this mobility edge and critical region. And there are, of course, special cases known as the generalized Aubrey-Andre model, where this self-duality still exists, but one can actually introduce this mobility edge. For this interesting finding, one can read this review article by a group of Subrata Mukherjee and others. However, recently in 2017, Das Sharma and group, they predicted that this mobility edge can still be found in a bichromatic lattice if you stay away from the tight binding Aubrey-Andre limit. So Aubrey-Andre model is a tight binding model where this atomic, the lattice sites are very, very deep. So what they propose is that if you keep your lattice depths very shallow and you are in the 1D bichromatic regime, then you can still find the existence of mobility edge or critical regime. So what they have proposed in this model is that there is a continuum Hamiltonian because it's not tight binding. So they have two different lattices. They can create this incommensurate potential. This is the primary lattice. This is the disorder lattice. So with this Hamiltonian, what they have obtained is that you can see that this dark patch is not directly going to this red patch at a particular value of BD. But what is happening here is that there is a patch here. You can see that if you go on increasing, if you go along the y-axis, you go through this localized state and to the extended state. So that means for this value of disorders, you have both extended and localized states. So this is the critical regime, and this line indicates the single particle mobility edge. So if you plot the IPR and NPR, average IPR and NPR for this case, you can see that there is a region here where both IPR and NPRs are finite. So that means the system is going from extended to all state localized via this region called critical region where both this IPR and NPRs are finite. Okay, so immediately after this proposal in the next year, in 2018, Emmanuel Bloch's group, they actually studied this model in their cold atom experiment, and they observed this phenomena. They observed the presence of this critical phase in the experiment. What they studied, what they tracked down is this density imbalance in their experiment and also edge density fraction. So if the states are localized, so what they observed is that this is a density imbalance between even and odd sides of the system. If the system is localized, then this quantity will remain finite in the long time evolution. And if the states are extended, then if you create a particle in the left side of the lattice, that will definitely propagate to the right side of the lattice. So this quantity will remain finite for the extended states in the long time evolution. So these are the theoretical predictions. So you can see that in the extended regime, D is finite and it vanishes in the localized regime where this I is becoming finite. But you have a nice intermediate regime where both these quantities are finite. And this is the experimental prediction on the right. So this is the critical region. And this is one of the very interesting and I think first observation of mobility edge or the critical region in cold gas experiment, in one dimension using cold gas experiment. Okay, so what is the summary so far? So what we have learned up to this point, we have learned that in one dimension there is no localization transition with true random disorder. However, if you introduce quasi-periodic disorder in 1D, that exhibits localization transition. For example, the Aubry-André model, the transition from all states extended to all state localized due to the self-duality condition, and the breaking of self-duality leads to the critical region where both extended and localized states are allowed, and that also gives rise to the existence of mobility edge. After the localization transition, all states remains localized no matter how strong the disorder strength is, and that is quite usual because if you increase the disorder strength, the states will remain localized forever. What you can see from here, once the states are localized like this, if you go on increasing this axis VD along this axis, they will remain more and more localized. This thing will become more red and red like yellow and so on. Okay, so is this last statement unique? Can we ask a question whether this statement is always true? So to see this, what we have done, we have considered a Doublewell lattice. So now, what is a Doublewell lattice? Doublewell lattice is a series of double wells where the particles experience two different hopping amplitudes. For example, T1 and T2, one is large, one is small. And when T1 is, at some point T1 is larger than T2, at some point you can make T1 smaller than T2. So this is called dimerized lattice, and depending on this dimerization, you may have different interesting phases in this system. So it was first discussed in the context of polyacetylene, and the model which describes this system is known as this very famous Schrieffer-Higger model or the SSH model, which is given by this. And this has two different sublattices, A and B, and these are fermionic creation and annihilation operators. So if you look at the energy structure spectrum of this, so you can see that the dispersion gives rise to interesting physics here. When T1 is greater than T2, you have a gapped dispersion, and when T1 is less than T2, you have another gapped dispersion. But if you go from T1 greater than T2 to T1 less than T2, at some point there is a gap closing region. Okay, so you go from a gapped region to another gapped region. through a gap closing point. Okay, so this interesting feature of this model gives rise to the topological property or topological phase transitions in this kind of SSH model. Okay, so this model preserves chiral symmetry. If you look at the band structure here, the band diagram, you can see that this delta is T2 over T1, that is a dimerization. This is the order control parameter here. If you look at this energies, you can see that this is a gap phase on this side when delta is less than 1. And on the other side, when delta is greater than 1, we have another gap phase, gap region. But only difference between this state, this region, and this region is that this region hosts 2 zero energy edge modes. Okay, so this is the difference between this and this. So this is known as the topological region. This is known as the trivial region. And this topological region possesses this edge states, which can be seen from this amplitudes at different sites. You can see these edge states are the amplitude at the edges are finite. However, if you go to this bulk somewhere here, you will see that the particle remains in the bulk. Okay, so this is the topological property of this Doublewell lattices. And what we are up to here is that we are going to study the effect of quasi-periodicity in this kind of SSH model or in this kind of Doublewell potential. So here we introduce the quasi-periodic potential in this along with this lattice. And you can see that this is nothing but Aubrey-Andre type potential, where we have separated the sublattice potentials like lambda A and lambda B. So in the limit T1 equal to T2 and lambda A equal to lambda B, we get back to our usual Aubrey-Andre model. So for T1 not equal to T2, the self-duality is broken. So that means this is no more same as real and momentum space. So what is the effect of disorder in such systems? Okay, so control parameter is delta, which is T2 over T1. When delta is less than 1, we have trivial phase. When delta greater than 1, we have topological phase. Now we explore the effect of lambda in both trivial and topological regimes by tuning delta. So we choose beta as this golden ratio and choose lambda A equal to lambda B equal to lambda. We call it as the uniform case when both these strengths are same. And we consider fairly large systems like 13,530 sites. And then we look for different diagnostics in the system. So these are the famous diagnostics we discussed, which is inverse participation ratio and normalized participation ratios. For delta less than 1, we have a gray patch over here where both NPR and IPRs are finite. And for delta greater than 1, we of course found some critical region where both NPR and IPRs are finite. So there is nothing surprising here because this is a self-duality broken system. So you get a critical region where both IPRs and NPRs are finite. Similarly, on the topological side also, we are getting the same critical region. So only difference in these two cases is that in the energy spectrum, where you can see that there is zero energy 8 states which appear in this case. There is no zero energy states on the trivial side. And eventually these zero energy states will become energetic and they merge into the hybridize into the bulk energies. Okay, so now this is not so surprising as I mentioned. Now we go to another case. So what interesting can be drawn from this kind of models? So what we have done, we just change this lambda A equal to minus of lambda B, that is equal to lambda. So what we have done is that in every alternate side, we change the strength of this sign of these lambdas. For example, in the first side, if it is lambda, second side minus lambda, third side lambda, minus lambda. So it's kind of staggered disorder case. So if we introduce this kind of quasi-periodicity in the lattice, then what happens in the system? So now I discussed about this topological part. I'll show the trivial part later. So for the topological part, that means delta is greater than 1. So what we have obtained is this figure. So here the IPR and NPR are plotted. Once again, we see a critical region. So what is surprising here? There is nothing. So you get this critical region posting a mobility edge. So the system goes from extended to localized through this critical region. Okay. So now what happened for different deltas? So if we go to different delta, now something surprising is happening here. So for delta equal to 2.2 or so, what we have seen here is that we are seeing something strange. We are seeing two gray patches. That means two critical regions. Okay, so for delta, for a critical delta, we can see that as a function of lambda, we can see two different critical regions. So that means in these two critical regions, I pairs and N pairs are finite. So this is something different which we did not see before. So this means what? This means this red line is IPR, is 0 and it becomes finite. That means at this point, this is finite and NPR is 0. That means one phase transition occurred. Okay, extended to critical to localized. After that, after some critical disorder, we can see that this NPR becomes finite, bringing in another critical region, and eventually another localization transition is happening here. So this is actually the interesting feature of this. Why it is happening, why this NPR is becoming finite again after certain critical disorder strength. Because if you plot the individual NPRs for individual states, you can see that these NPRs are becoming 0 at some points here in some region, and then suddenly some of these NPRs are becoming finite. The NPRs of some of the states are becoming finite, and this gives rise to this small peak in this NPR, and that gives rise to the second critical region in the system. Okay, so this is indeed something interesting, and to verify that whether this peak, small peak over here, is really a peak or it's a finite size effect, what we have done here is that we have performed this finite size extrapolation. And when we extrapolate this L to infinity, you can see that for different system sizes, as you go on increasing the length for L equal to infinity, you can see that the NPR is becoming 0 in this regime of disorder. And then it is becoming finite, and finally it is becoming 0. So this is the 1 over L plot of NPR. You can see that for 1.5 it is going to a finite value, then for 2 it is vanishing, then 2.5 it is finite, and then eventually it is vanishing. Okay, so this is the confirmation of reentrant localization transition. So let me explain this to you with some further physical quantities. How can you see this in other quantities such as energies and eigenstates? You can see that this energy versus lambda superimposed with their IPR values. IPR, this is red meaning IPR equal to 0, blue meaning IPR equal to 1. So you can see that this straight line, this line here, tilted line here, that actually separates, that indicates the mobility aids. So up to this point, all states extended, and in this region, there are extended as well as localized states, and in this regime, only localized states, and somewhere here there is a red patch which is visible here, where some states are becoming extended again. Okay, so this is the reentrant feature, which can be clearly seen in this eigenstate index with their IPR values. So up to this point, these are all extended, and this regime is extended plus localized. And from here to here, this region is localized, and this red patch which is reappearing, that means some of the states are becoming extended. Okay, so we are going from extended to critical to localized, critical then localized. Okay, so the previous notion that when lambda becomes larger and larger, all these states remain localized after the first localization transition, it is no more correct. So we can enter into another critical region, and localization can happen again. Complete localization can happen again for larger disorder strengths. So we verified this for particular state, by plotting the IPR and NPR for a particular value of lambda across this point and across this region. So we can see that extended and localized states are separated here. So this indicates the critical region in this area. Okay. So we also see similar signature from density of states. Now, to summarize this physics, we obtained the phase diagram of both uniform disorder case and staggered disorder case. To obtain the phase diagram, we obtain this. We compute this quantity called eta, which is a log of IPR into NPR, which was actually proposed in this paper of Das Sharma. So you can see that in this phase diagram, this quantity eta is plotted along the z-axis. This color indicates the value of eta. So in the localized and extended states, this eta value is similar. They are all close to -4, and this blue region indicates the critical phase. Okay, so this delta equal to 1 line, this is the Aubrey-Andre limit. So you don't see any critical region. It's all red. it goes from extended to localized. But as you move away from this self-dual point, you can see this critical regime is appearing. So on the other side, in the in the trivial regime also you see a critical phase. In the topological regime, you see a critical phase, and the transition happens from extended to critical to localized. But if you go to staggered case, you see this interesting feature over here. There, after some critical delta, you see this reentrant feature. So the system goes from all state extended to critical, then all states localized, then to critical, then all state localized again. So this is a reentrant localization transition. So the system is system is getting localized twice. So it is getting localized first here at this point, and then entering a critical phase, then getting localized again. So this is happening in topological regime. And you can notice here in the trivial regime, when delta is less than 1, there is no concept of edge states and all. Here also you still see this reentrant feature. So that means topology has no role to play in this kind of reentrant localization transition. Okay, so this is the delta equal to 1 line where there is this is the Aubrey-Andre limit. There is no critical regime. But on the both sides, you see this localization transition after some critical values of delta. Okay, so this was the finding. If I have, do we have some time here or?
Yes, you have 5 minutes.
Okay, 5 minutes. Okay, fine. Yeah. So after finding this reentrant feature in this model, so what we have done, we looked for some experimental signatures of this kind of physics, and we looked for the signatures in the quantum walk of this model. And quantum walk is one of the very interesting or useful tool to understand the physics of some system in a dynamical way, in the dynamical evolution of some initial state. This was actually discussed in great detail in the talk of Emmanuel Bloch, where they have used to predict many different interesting physics using this physics of quantum walk. So here what we do is that we create some initial state, and then we unitarily evolve it with respect to the system Hamiltonian like this. And using this time evolved state, we compute some observable expectation, and looking at this observable, one can see the behavior of, predict the behavior of this quantum mechanical state. So here what we have done, we have created a particle at the middle of the lattice, and then we time evolved it. And here we are plotting the density evolution in the quantum walk. So what you can see is that for lambda equal to 0, that means no disorder. There is a very, pre-particle evolution. This spreading is like, you can see a ballistic type expansion here. But as you go on increasing the value of a disorder strength, you can see this profile is getting decreased. It is slowly narrowing down. And then as you reach this lambda equal to 2 point, which is somewhere here. So I am going like this. I am going along this line, delta equal to 2.2. So I am going from extended to critical to localized. So you can see for lambda equal to 2, there's a very narrow profile here. That means it's a localized phase. And as you increase lambda, so you enter into this critical regime where this profile has to expand. So it's a slight expansion over here compared to this one for 2.5 and 2.8. And then for very large value of lambda, then you enter into this localized regime. Then again, you see this localized profile. And for large and large value, you get this localized profile. So this is kind of a reentrant phenomena. You go from extended to critical, then localized, then critical, and then localized. So this localization is happening twice. So this is why it is called reentrant phenomena. We also observe this root mean square displacement in this evolution. Root mean square displacement, which is computed like this. You can see that for lambda equal to 0, it's a ballistic expansion. As you increase lambda, you see this is slowing down, and you can see the reentrant feature here. For lambda equal to 0, 1, 2 is here, the green one, then it increases for 2.8, then again goes to 3. So it's like reentrant, blue, orange, green, red, and purple. Okay, so this is again the reentrant physics here. So we also compute this edge density fraction, which was experimentally observed in the experiment of Emmanuel Bloch. So we can see that this H density fraction for extended state is 1, then it is decreasing, then for lambda equal to 2, for completely localized state, it is 0, for critical, it is becoming finite, and then becoming 0. So it is again reentrant, finite, finite, 0, finite, 0. So reentrant feature is visible in this experimental quantity, which can be seen in optical lattice experiment. And then we look for the effect of topological edge state on this reentrant transition. So we plot this edge state behavior here in this graph. You can see this feature here. The energies are 0 for these two states for lambda equal to 0. And as you go on increasing lambda, these states actually go and hybridize into the bulk. And one of the state hybridizes first, and then the second one later. And this is the point where this gap closes. So if you look at the IPR of this state, which hybridizes first, you can see that there is a reentrant feature here also. The IPR is finite because the state is initially localized. This is a localized edge state. Finite to 0, then finite, 0, and finite. So this is another reentrant feature, but this reentrant feature is happening somewhere far actually, somewhere here, not close to where it is happening. So it is actually happening far from the band gap closing. So therefore, this has no contribution on the reentrant localization we are seeing here. This entire reentrant localization is happening due to the bulk state, not due to the edge state. So the edge has no role in this reentrant feature. Of course, they have their own reentrant properties. So here we plot the states, the amplitudes here for both these edge states. So here one is localized in the left end of the lattice, other is localized at the right edge. And then as you go on increasing lambda, one of the states gets hybridized to bulk, so it becomes delocalized. So you can see it is getting delocalized, and then localized, then delocalized, then both of them gets localized. So somewhere here, localized, delocalized, localized, delocalized, localized. Okay, so this is the again reentrant feature of the edge states, and this is all I wanted to say. This is the summary. So what we have done is that we studied the localization transition in a quasi-periodic Doublewell lattice. While the presence of uniform quasi-periodic potential leads to one critical region, staggered quasi-periodic potential exhibits reentrant localization. For a range of hopping dimerization, the system goes from extended to critical to localized, then to critical, and then finally to localized phase. So edge states also exhibit reentrant phenomena, but they have no contribution for this bulk spectrum. So what can be done further? You can study the effect of interaction in the context of many-body localization. And can this many-body localization exhibit a second critical regime? And one can also study the topological properties in presence of this disorder, and so on. So my co-workers are Professor Sourav Basu, my colleague here in the department, and the PhD students Silpi, Ashirvad, and Suman, and Professor Bilal Tanatar from Bilkent University in Turkey. And thank you very much for your attention.
Thank you very much for a very interesting talk. Now this talk is open for questions or comments. Now there is one question from Kanaya Pandey. So Dr. Pandey, you can unmute and ask the question.
Yeah, so what I'm asking that about this super lattice you were talking about, that there are two lattices which are exactly, one is exactly in the center. So for example, you can make this kind of lattice using 1064 and 532 nanometer. But
yes, yes.
Many times, you know, it's for example, we are not having 532 nanometer. We are having, for example, 800 nanometer. So what will be the situation in that circumstances?
No, in that case, you mean this to get this lattice in your lab, you have to actually use one of the lattice. If one of the wavelength is lambda, the second one will have to be lambda by 2. Otherwise, you cannot get this exact Doublewell structure.
Yeah. But it is not exactly that. That's why I'm asking that what will be the situation in that circumstances?
Okay. So in that situation, yeah, so we are actually exploring that situation. If your lattice is not exactly like Doublewell, so we are exploring that situation, and we are getting some interesting features there in the reentrant, in the context of reentrant phase transition. So what we are getting is, I don't want to disclose it here, but briefly I can give you some hints. So we are getting multiple localization transition in this kind of lattices. So in principle, I mean, this kind of double-well lattice, what I'm going to say is that this kind of double-well lattice is not necessary to see this re-entrant phase transition. One can actually have other lattices where this kind of re-entrant transition can occur. And what you have rightly mentioned, that if you have a 1064 nanometer lattice and you have 800 nanometer lattice, we can certainly see some re-entrant phase transition when your lab comes up. We'll definitely propose our theory to see some interesting re-entrant localization transitions. That work actually going on is an ongoing work, so I don't want to highlight detail on that.
Okay.
Yeah. Basically, this physics is due to the competition between the disorder strength and the kinetic energy in the system. So, if you can define some system where this disorder strength can dominate over the kinetic energy at some particular value like this, then this re-entrant physics can appear.
Okay.
Yeah.
So, if there is no more question, so let us thank the speaker for the excellent talk.
Yeah.